Okay, we're going to start talking about machine learning today. In particular, we're going to talk about a still popular form of learning called decision tree learning. And this is coming back into style because I'd say every 10 years, simulated neural net learning becomes popular again, and then it fades away. Now it's called deep learning. And if you want to read more about deep learning, artificial neural network learning, it's certainly in the book, our book, and you can find it elsewhere. But one of the problems with artificial neural network learning is that the results of the learning are mysterious to humans. A human can look at the recommendations of a deep learning algorithm and not understand how it's coming to its conclusions about what it should be doing. And needless to say, physicians are not keen on acting on recommendations that aren't comprehensible to them, and neither are other professionals. And so there is now an area of machine learning which didn't used to have to be the case because much of machine learning was this way already, called explainable machine learning. And that is machine learning that can actually explain why it is it's recommending what it's recommending. And decision tree learning is one of those kinds of machine learning that present human analysts with a comprehensible explanation or representation of what is learned. There's two perspectives on machine learning. One is that it's a kind of advanced data analysis. So a human analyst might use machine learning methods much as a practical statistician would use statistical methods to come up with models for the data and predictions from the data. But it's also traditionally in artificial intelligence as a mechanism for endowing our artificial agents with the ability to adapt from experience. You'll see graphs like this. These are called learning curves. As a machine learning system is trained with increasingly large amounts of data, its performance on some tasks changes. And presumably, it changes for the better. It increases. In some cases, though, it may remain relatively flat. In other cases, it may increase and then get worse as a result of what the book calls overfitting and what is traditionally called overfitting. And we'll talk briefly about that later. But generally it increases. So if performance quality, what we were measuring here, was accuracy, we would expect increases. And many times learning curves follow this characteristic of rapidly diminishing returns. You get better with a little bit of data. You get quite a bit better with even a little bit of data. And then you increase the machine learning system, AI system, increases its performance, but with fewer and fewer returns. We'd also might be measuring, rather than prediction accuracy, we might be measuring its inverse, error rate, or perhaps something like response time, in which case we would expect, in the ideal case, that the learning curve would be decreasing as response time decreases or error rate decreases. You become better and better to task. There are different biases that I would say are present in different learning algorithms. I call these pessimistic biases and optimistic biases. In an optimistic bias, you are sort of jumping quickly to conclusions. You can see an instance of a Scotty dog and an instance of a German Shepherd, and my guess is most of you could tell the difference between any Scotty dog and any German Shepherd after that, having seen only one instance of each. And if you can do it, the machine learning system can do it too. But it's following a what I would call optimistic bias. It's saying there's a great deal of information in the instances we're seeing about the world, and systems that are designed to be optimistic about the data are going to jump to conclusions, and they'll very often be right. A pessimistic bias is just the opposite. It may require a lot of data to actually reach conclusions. Deep learning systems, for the most part, are pessimistic. They require a lot of data to see things. Approaches called instance-based learning are very quick to jump to conclusions, and they need very little data to start performing very well. So there is a lot of different kinds of machine learning methods. And right now, we're just talking about supervised machine learning methods. That's what the chapter that you've been reading is talking about, supervised machine learning systems. And it's probably going to be the only one we talk about in class, at least in any depth. And the idea in a supervised machine learning system is we've got roughly a setup like this. An agent is making observations in the environment. An agent may have some existing knowledge in a knowledge base that it can use to help it learn, but it's also got to perform at some task, and I've just called this the performance component. This varies a little bit from the figure in the book in some of the details, but you can see a similarly intended figure in the text on machine learning. But the idea is that we have a classifier, and today we're going to be talking about decision tree classifiers. And this was optional reading for you. If you do want to go and read in section 7.3 about decision trees, you can, but I think we'll cover most of what is covered in the book, at least what I'm going to hold you responsible for in lecture. So we have an example of a decision tree, which is an example of a classifier. We're going to get observations about the world, and these observations are going to come in the form of a feature vector, a set of values about an observation. And we'll see an example in just a second. Here you can see this is a movie reviewing application. And it might be of the kind that Netflix might record for me. But we're going to get a set of features. These are sometimes called independent features. And the job is to predict some outcome for this, some classification for this. So in the case of the movie recommendation system, this would be rent it or watch it. That would be one class, or don't rent it and don't watch it would be another class. These would be the two classifications. And given characteristics of the movie or the object, we're trying to predict a class. Is this something Doug will want to watch or not want to watch? This is fed to this performance component, which accesses the classifier and gives a prediction about what the classification for that previously unlabeled datum was, and then sends it back to the environment. So supervised learning is going to be learning to associate a vector of independent features, typically a vector, with two or more outcomes, typically. At least two outcomes. And in all the cases today, we're going to be talking about only binary valued features, and we're going to be talking about binary valued classes, but this generalizes quite easily to the case where a variable can take on multiple values and the classification can take on multiple values. So here's an example of a decision tree. Ebert and Siskel are historically my favorite movie reviewers. They're both dead now, so I can't use them anymore except on historical data. But you can think of this, you can think of Ebert and Siskel as perhaps your doppelgangers on Netflix. You have never met Siskel and Ebert. They are persons that access Netflix and watch movies on Netflix who you have never met. But Netflix knows that your movie watching behavior and your preferences are very like theirs. I'm guessing that Netflix does this. I don't know for sure. Netflix has not told me what their recommendation system does. But certainly if I was Netflix and I had millions of people accessing my site, I'd be looking for doppelgangers. Okay? I'd be looking to see if Chandler was a close match to Doug, and I would use his predictions possibly to make predictions about me. Now, usually, this is related to an idea called collaborative filtering, where you're actually taking a look at my behavior and you're matching it against a large population of people's behaviors. And you're not matching very often against one person, but you're matching against a group of people who behave like you. And beyond that, you're abstracting away from individuals altogether, and you're looking for correlations between movie preferences. So you might often see when you go on looking at books or movies or something else, people who like this also like this. And we think you might like this because you like this other thing. That's called collaborative filtering. It's sort of looking at your behavior, comparing it to a population of behaviors, and then making predictions based on it. But let's say in general, Netflix is maintaining a classifier for me. They have built a classifier that's just for me. And they built a classifier that's just for Matthias and Marion. And so we have these classifiers, one for each of us. And this is my classifier. If Ebert does not like a movie, I might go down this path and look at this subtree. If that movie is a sci-fi movie, I might go to this node. I would go to this node next. If there is a big star in that movie, I might decide to rent it. So if Ebert does not like it, but it's sci-fi and there's a big star, I rent it or I watch it. That's the recommendation system, the recommendation I may get. If Ebert does like the movie and Siskel likes the movie and it's a romance and it's in black and white, I watch it. If these features are still true, I come down this path and it's not in black and white, I don't watch it. Okay? So Ebert, yes or no, recommends. Siskel, yes or no, recommends. Suspense, yes or no. Romance, yes or no. All of these are characteristics of movies that might exist in Netflix. So here is the unlabeled data in blue, and the question is, do I rent it or not? This is something that Ebert does like. Siskel does like it. You can look at that feature. It is not a romance. I rent it. I watch it. Here is a different vector, but with some shared values. Ebert recommends, Siskel recommends. It's not it is a romance in this case, and it is not black and white, and so I would go down this different path, and I would choose not to rent it. Still another vector that's unlabeled. I want to make a prediction. This is a sci-fi that Ebert does not recommend. It has a big star. I decide to rent it or watch it. Okay, so you get the picture. Decision tree is a very simple data structure. You give it a unlabeled datum like this, and it will make a prediction about the classification. And the classifications are all given at the leaves of the decision tree. So how do we learn these decision trees? All right, we have this data structure that's pretty straightforward. How do we learn them?